I'm Mahika Kalthe. Welcome you all to my low speed aerodynamics ISC2 video presentation on the topic of vortex filaments. So, in this presentation, we'll be seeing the following contents: what is vortex in aerodynamics, what is vortex filaments, vortex sheet representation, and Biosavit's law. So let's move on to start. The first thing is, what is vortex? A vortex in aerodynamics is a rotating column of air that forms behind a wing or other body that generates lift. Wingtip vortices are the most common type of vortex in aerodynamics, and they are caused by the difference in pressure between the top and the bottom of the wing. So now let's move on to the effects that cause vortices. The first is drag. Vortices can create drag, which can make it more difficult for an aircraft to fly. This is because vortices disrupt the airflow around the aircraft, which can increase the amount of energy required to keep the aircraft flying. The next is lift. Vortices can also reduce lift, which can make an aircraft more likely to stall. This is because vortices can create a pressure difference between the top and bottom of the aircraft's wings, which can reduce the amount of lift generated by the aircraft wings. Stability. Vortices can also affect the stability of an aircraft. This is because vortices can create a moment that can cause the aircraft to roll or pitch. Noise. Vortices can also create noise, which can be a nuisance to people on the ground. This is because vortices can create a whistling sound as they pass by. Now, moving forward, let us see the ways to reduce vortices. The first is winglets. Winglets are small extensions on the tips of the aircraft wings that can help to break up the airflow and prevent the vortices from forming. Stall strips. Stall strips are small strips of metal that are attached to the leading edge of the aircraft wings. Stall strips help to delay the onset of the stall, which can reduce the amount of lift that is lost due to vortices. In the image, we can see a stall strip attached on the leading edge. The next is flying at higher altitudes. The air is thinner at higher altitudes, which makes it more difficult for vortices to form. Flying at lower speeds. Flying at lower speeds will reduce the amount of lift generated by the aircraft's wings, which will also reduce the amount of vortices that are formed. Now, moving on to vortex filament. So, what is a vortex filament? In general, a vortex filament can be curved as shown in the figure. The filament induces a flow field in the surrounding space. If the circulation is taken about any path enclosing the filament, a constant value is obtained. In this figure, we can see a vortex filament of strength tau, and a point P is placed at a distance r from the vortex filament. Now, moving on, the strength of the vortex filament is constant along its length. This means that the amount of vorticity, that is, a measure of the rotation of the fluid, is the same at any point along the filament. Vortex filaments cannot end in a fluid, they must either form a closed loop or extend to the boundary of the fluid. This is because of the vorticity would have to become infinite in a vortex filament ended in a fluid. Here in the diagram, we can see a clear-cut vision of the vortex filament. Now moving on to vortex sheet representation. Firstly, what is a vortex sheet? Now imagine an infinite number of straight vortex filaments side by side as shown in the figure, where the strength of each filament is infinitesimally small. These side by side arrangement of vortex filaments forms a vortex sheet. Here we can see how the vortex filaments are arranged side by side, and in the adjacent figure we can see the edge view of the sheet. Now let us see how the vortex strength is represented. Let S be the distance measured along the vortex sheet in the edge. Definitely, Gamma is equal to gamma s as the strength of the vortex sheet per unit length along s. Thus, strength of an infinitesimally small portion ds of the sheet is ds. This small section of the vortex sheet can be treated as a distance vortex of strength gamma s. Now, consider point P in the flow located at a distance r from ds. The Cartesian coordinates of P are x and z. The small section of the vortex sheet of strength gamma ds induces an infinitesimally small velocity dv at point P, and dv is given by minus gamma ds upon 2 pi. Now, moving on to the last part, that is Biot-Savart's law. In aerodynamics, Biot-Savart's law is used to calculate the velocity field induced by vortices, which are rotating columns of air. Vortices are created by the flow of air around aircraft, and they can have a significant impact on the aircraft's performance. Here in the image, we can see that the vortex filament of strength tau, and also the velocity is given, which is equal to dv, which is equal to gamma upon 4 pi dl into r upon r cube, where r is the distance from the vortex filament to point P, which is at a distance of r. Here are some of the applications of Biot-Savart's law in aerodynamics. Designing of an aircraft. The Biot-Savart law can use to calculate the velocity field induced by vortices around aircraft. This problem can be used to design aircraft that are more efficient and less likely to experience vortex related problems. Understanding vortex induced vibrations. The Biot-Savart law can be used to calculate the velocity field induced by vortices around objects. This information can be used to understand the dynamics of vortex induced vibrations, which can be a problem for aircraft and other structures. Modeling the flow of air around obstacles. The Biot-Savart law can be used to model the flow of air around obstacles. This information can be used to understand the effects of obstacles on the flow of air, such as the forming of vortices. With this, we conclude to the video. Thank you.